Welcome to class. Happy almost Halloween. Let's get started with some pre-calculus. Pre-calculus. Thank you. All right, so today we're talking about graphing rational functions. And I'm just going to start off by saying a lot of the things we're going to do to graph a rational function are the same things we did to graph polynomials last time. So we're still going to find x-intercepts, we're still going to find y-intercepts. We're still probably going to talk about the multiplicity of the x-intercept. So there's a lot of similarities in graphing rational functions versus polynomials. Also, one of the reasons that's true is because a rational function is just some polynomial divided by some other polynomial. So here are some examples of rational functions. F of x equal to x squared divided by x to the 6 minus 1. It's a polynomial on the top, it's a polynomial on the bottom. F of x equal to x squared plus 1 over 3x squared minus 1, both polynomials. And f of x equal to 4 over 3x squared minus 1, both polynomials, right? 4 is not a very interesting polynomial, but it's still a polynomial. So it's definitely a polynomial divided by another polynomial. And that's all a rational function is, just one polynomial divided by another polynomial. I will say typically the polynomial in the denominator should be of degree 1 or larger. If you had a polynomial like this, or sorry, if you had a rational function like this, say g of x equal to x squared plus 3 divided by 4, I wouldn't really call that a rational function. I would call that a polynomial, because you could rewrite that as 1/4 x squared plus 3/4. So if your denominator is just a constant, it's not really a rational function. But that's not something we need to worry about. And like I was saying, we can use a lot of our techniques for graphing to help us graph this, like finding x-intercepts, finding y-intercepts, drawing number lines. There's a couple of extra things we have to talk about. This is specifically asymptotes. So rational functions won't always, but will often have vertical and or horizontal asymptotes. The nice thing is that they're not too terrible to find. Welcome. Thanks. So for vertical asymptotes, they're going to be vertical lines, right? That's why they're called vertical asymptotes. And they're going to be written as x equal to some number. And here's how we're going to find them. We're just going to set the denominator equal to 0. And solve for x. So a couple examples. Maybe an example. Let's say our function was x squared plus 1 over x plus 2 times x minus 3. To find the vertical asymptotes, we're just going to set x plus 2 times x minus 3 equal to 0. And we're going to solve, and we're going to get x equal to -2 and x equal to +3. And those are both going to be vertical asymptotes. Now, you might be wondering why these are vertical asymptotes. Well, the reason is because as x gets very, very, very close to +3 or to -2, the function value gets extremely large. So if you think about plugging in a number that's really close to 3, like let's say we plugged in 3.0000001. The numerator is essentially 10. Right? 3 squared plus 1 is 9 plus 1, which is 10. And the denominator is a very, very small number. And when you divide by a very, very small number, the fraction gets very, very large. So at x equals 3, the function values are getting super big or maybe super negatively big. And so that's what having a vertical asymptote looks like, because as the x values get closer and closer to 3, the y values would get further and further up or further and further down. So it's kind of it's a little bit of a thought process there, but in the end, it's really, really easy to find them. All we're going to do is set the denominator equal to 0 and solve. There's going to be one little exception later on, which we'll talk about, but for now, that's really it. So as far as vertical asymptotes are concerned, the only time a function has a vertical asymptote is when you divide by 0, or if it's a logarithmic function. Right? We talked about logs before. Logarithmic functions have vertical asymptotes. They're like the only kind of special function that has a vertical asymptote where you're not dividing by 0. Every other function has a vertical asymptote. you get it because you were dividing by 0. This function, right, if you plug in x equal to -2, you're going to get 5 over 0. And if you plug in 3, you're going to get 10 over 0. And that quote unquote division by 0 is the problem. That's going to make the function blow up. It's going to be really large or really negatively large. And it's going to have a vertical asymptote there. So as far as we're concerned, we're just looking for where the denominator is equal to 0. Generally, functions never cross their vertical asymptote since no y value is possible for those particular values of x. I will say the one exception to that rule is for piecewise functions. Like I think there was a homework problem where you had a piecewise function where there was like a little point on the vertical asymptote. That's okay, that can happen sometimes. So vertical asymptotes are relatively easy to find. Horizontal asymptotes are a little bit more work. So here's kind of the process. To find horizontal asymptotes, there's 3 different things. Well, there's one thing to consider, and then there's 3 different outcomes. So we're going to consider the degree of the top and bottom. Remember, the degree is just the highest power of the highest power of x in each polynomial. So one possibility is if the degree on top is less than the degree on the bottom. If that's the case, then the horizontal asymptote is y equal to 0. A couple examples of this, excuse me. Y equals 1 over x, or f of x equal to 2x over x squared plus 1. Those are both examples of where the degree on top is less than the degree on the bottom. For this first example, let me see a little bit. I feel like you guys have trouble seeing that. For y equals 1 over x, what's the degree on top? And that's tricky. Let me ask you. For x, what's the degree on the bottom? 1. So what's the degree on the top? 0. Right? There's no x's. There's 0 x's. The degree is 0. The degree on top is less, and we've definitely seen this function before. Y equals 1 over x. It for sure has a horizontal asymptote of y equal to 0. And that's really because as the x values get super duper large, the y values get close to 0. Or as I like to think about it, the denominator is way bigger than the numerator. The same thing is true for this function. As x gets really, really big, sure, the top and the bottom are both going to be large, but the bottom is way, way bigger. Right? The bottom is a much, much bigger number. Like if x is 1,000, the numerator is 2,000, the denominator is 1,000,001. 2,000 divided by 1,000,001, super small. And it's just going to get smaller and smaller as x gets larger and larger. So if the degree on top is less than the degree on the bottom gets bigger faster, and the fraction gets really, really small, close to 0. The second possibility is if the degree on top is larger than the degree on the bottom. If that's the case, then there is no horizontal asymptote. It's kind of the reverse of what we just said. Instead of the fraction getting very, very small, the fraction is going to get really, really large. And it's going to get infinitely large, and it's not going to get close to any one particular number. And that's what it means when we have a horizontal asymptote, is that as you go further and further to the right, the function gets close to one particular number, like y equals 2 or y equals negative. Or as we go way, way to the left as well. So if the numerator is getting bigger, the fraction is getting large, the function's either blowing up, or it feels weird to say blowing down, but like, right, it's going very, very negative. Those are the possibilities. And then thirdly, what we're going to see most of the time is that the degrees are equal. So if the degree on top is equal to the degree on the bottom, then the horizontal asymptote is a little complicated. It's y equal to the leading coefficient of the top divided by the leading coefficient of the bottom. So an example of that, the second function we wrote up there, f of x equal to x squared plus 1 over 3x squared minus 1. Are the degrees the same? Are the degrees the same? What? Let me ask. What's the degree on top? What's the degree on the bottom? Also 2. The degrees are the same. What's the leading coefficient on the top? What's the leading coefficient on the bottom? Awesome. So the horizontal asymptote would be y equal to 1/3. And that's because what's happening here is the x squared on top and the x squared on the bottom are essentially growing at the same rate. And so this fraction is going to get closer and closer and closer to 1/3. Again, if you plugged in something large like 1,000, you would get 1,000 squared plus 1, which is 1,000,001, divided by 3 times 1,000 squared minus 1, which is 3,000,000 minus 1, which is 2,999,999. And I don't want to plug that into my calculator, but if you did, I'm darn sure it would be very, very close to 1/3. Maybe 0.333, a lot of threes. Eventually, it would be something that wasn't a 3, because it's not exactly 1/3, but it's very, very close. That's the whole idea. For a horizontal asymptote, as the x values get big or negatively big, the y values get close to some number. In this case, y equals 1/3. So vertical asymptotes, somewhere in the middle, if you have division by 0, you've got a vertical asymptote where the function's either getting really, really large or really, really negatively large, or it could be like this, right? This one side could go big and one side could go small. For horizontal asymptotes, you're going way out to the ends. And you're saying, okay, if I go way to the right or way to the left, what's the function getting close to? And the way we find those things are the way we've just talked about. In vertical asymptotes, you're looking for where is the denominator equal to 0. Horizontal asymptotes, you're looking for, well, it's a process, right? You have to compare the degrees, and then if they're the same, it's the it's the quotient of the leading coefficients. Leading coefficient at the top divided by leading coefficient at the bottom. Degree on top is smaller, horizontal asymptotes here. And if the degree on top is larger, well, we'll talk about that more next class, because there is kind of a special expert case that we'll talk about next time. Slant asymptotes, if you've ever heard of them, is what I'm referring to. But that's for next class, not for today. All right, let's look. I got kind of cut off. That's too bad. That'll be fine. Let's look at some examples. So before we get to the asymptotes, let's look at actually see the example maybe. Let me zoom back out just a tiny bit. So before we get to the asymptotes, we should consider the usual things. So when I'm graphing a rational function, I'm going to start with my usual, in fact, any function. I'm always going to start by finding the intercepts. That's always kind of my go-to. So I'm going to start with the y-intercepts. Okay. So in this case, which we get by setting x equal to 0. So I set x equal to 0. I'm going to get f of 0 equal to 0 plus 6 over 0 minus 2, which is negative 3. Great. So my y-intercept is 0, negative 3. X-intercept, same sort of deal. We're going to set y equal to 0. So if I do that, so it's a little more work. Actually, it's not really that much more work. So here's something that is worth knowing. You set a fraction equal to 0. Well, in fact, let's just do it. What should I do to solve this equation? What should I multiply both sides by? Right. Or more generally, the denominator. We multiply both sides by x minus 2. What am I going to get on the left? 0. What am I going to get on the right? X plus 6. This is always going to happen whenever you're setting a rational function equal to 0. After you multiply both sides by the denominator, you're just going to have the top equal to 0. You can shortcut that, right? You can just start with, oh, it's rational. I know for a fraction to equal 0, the numerator has to equal 0. The only way you can get a fraction to equal 0 is to have 0 divided by something that's not 0. So the top has to be 0. Solving this, we get x equal to negative 6. And it is worth mentioning here that the top is 0 and the denominator is not. There's kind of a special case where both the top and the bottom are 0. I don't think we're going to get into that today, but I'll just warn you that it's something that can't come. What that really says to us is we should do some factoring if we can before we do any of this. This one obviously didn't factor at all, right? There's nothing to factor on the top or the bottom, but we'll address that in some future examples. So, okay, we've got our x-intercept. All right, and I should write it as right, -6, 0. That's my x-intercept. And then we're finally ready to talk about the asymptotes. And for no particular reason, I usually look at the vertical asymptotes first and the horizontal asymptotes second. I don't know why, that's just how I've always done it. So we next look at the vertical asymptotes. And we're going to get those by setting the bottom equal to 0. Oh, and there was something let me back up for just 1 second. I should also mention that just like with polynomials, x-intercepts for rational functions do have a multiplicity that has the same sort of behavior. So if you look at this x-intercept, -6, which came from setting x plus 6 equal to 0, I know it's not there, but there is a power of 1, which means our x-intercept has what kind of multiplicity? Odd or even? Odd, right? I was like, right, so x-intercept, this has a multiplicity of 1, which means we're going to bounce or cross. Ooh. We're going to cross, right? When it's odd, we cross because we change signs. So, good idea. For the vertical asymptote, we're going to set the denominator equal to 0. So we're going to set x minus 2 equal to 0. We're going to get x equal to 2. That's our vertical asymptote. And for our horizontal asymptote, we're going to look at the original thing. So I look back at y equals, I should say. So horizontal asymptote, right? That's the one that's like a lot of words to write. I'm going to say, look at the degrees. So if I look at my original function, x plus 6 over x plus 1, sorry, x plus 2, the degrees are definitely the same, right? The top is a first degree, the bottom is a first degree polynomial. It says, oh, is that? Oh, yes, thanks. Sorry about that. Good call. I would have been really confused when I started graphing this. The degrees are the same, they're both 1. So the horizontal asymptote is going to be y equal to 1 over 1. Right? The coefficient on the top, the leading coefficient on the top divided by the leading coefficient on the bottom, which is just 1. You don't need to write that step, but I wanted to show you. So you're like, oh yeah, I know it's the quotient. And now we're going to throw it all on the graph. So I'm going to have a y-intercept of -3, an x-intercept of -6, a vertical asymptote of x equal to 2, which we typically draw as a dashed line. And a horizontal asymptote of y equal to 1. And now, personally, so for these, you can't really talk about, well, I mean, you can talk about end behavior, but the end behavior is also what the horizontal asymptote is. Right? The horizontal asymptote is really telling you what the end behavior is. There's no like additional end behavior to consider. And now we kind of have to, you can do this a number of ways. I personally like to just graph it from meaning, and this is a kind of an important thing. You can only cross the x-axis where you have an x-intercept. Let's say that again. You can only cross the x-axis where you have an x-intercept. And sometimes you don't even cross the thing because you bounce. So the only time this graph can even touch the x-axis is right there. So if I have to be below the x-axis here, there's no way I can jump above it between here and there. So I know the graph has to kind of do this. There's no other choice. Now, as I continue towards my vertical asymptotes, am I going to go really, really positively large or really, really negatively large? It has to be negative. It can't be positive because I can't cross the x-axis. I will tell you all, I could cross the horizontal asymptote. That is not a barrier. You can definitely cross horizontal asymptotes. We will cross some later, I promise you. Horizontal asymptote isn't the thing that says don't cross me. Don't cross me. It's the thing that says you get close to me as you go way out this way or way out this way. But in the middle, all sorts of crazy stuff can happen. So horizontal asymptotes are not a barrier that we cannot cross. You can totally cross a horizontal asymptote. Sometimes you don't. Right? In this graph, we're not going to cross it, but there are graphs we totally do. Okay. And then on the other side of this vertical asymptote, am I down here or am I up here? Well, there's a couple ways to decide this. You could either logic it out and say, well, I can't be down here because then I would have to go up this way and cross the x-axis so I could get close to the horizontal asymptote. That's not going to happen. So I have to be up here. But probably the easier way, instead of trying to I mean, logic is good. It's good to think about these things. But the easier way to do this would be pick another point. Right? I'm going to plug in x equal to 3 because 3 is right there. And f of 3 is going to be 3 plus 6 over 3 minus 2, which is 9 over 1, which is 9. It's probably the faster way of handling that. So up here, we got some y value of 9, and then it's going to do this kind of deal. Now, I haven't really graphed the whole thing. I've graphed almost the whole thing. But I forgot about this little section over here, right? I don't just stop at that x-intercept. I cross the x-axis and keep going and getting closer and closer to my horizontal asymptote that way. Yes, I do have a cow costume. Yes. Yes, you need the whole thing. Yeah, and so I'm not saying you have to plug in x equal to 3 to find what's going on here. I'm saying, well, you can. You don't have to plug in anything though. You could totally deduce that the graph has to be up here because it cannot do this thing here. I'm a fan of plugging in more points. I think it's a good idea, but you don't have to. Other questions? Yeah.
Is there a way to know if it crosses the horizontal asymptote?
Yes, there is, but we're not going to worry about it. So here's how you could tell if it crossed the horizontal asymptote. What is the horizontal asymptote in this particular one? -1, right? And the way you would know if it crossed it is if the function was ever equal to 1. So if you set the function equal to 1, x plus 6 divided by x minus 2 equal to 1, there's not going to be any solutions there. X plus 6 and x minus 2 are never equal to each other. So their fraction's never going to equal 1. Or you could multiply both sides of x, right? That's the easier way. Multiply both sides of x minus 2. X plus 6 equals x minus 2. Oh, not going to happen. But that's in general how you check to see if you cross your horizontal asymptote. If you set the function equal to the horizontal asymptote and then see if there's any solutions. We're not going to worry about it too much though. Because what we're going to see for a lot of examples is we're going to get forced to cross it or not. All right, let's look at another example. Oh, we got loads of time. Loads of time. I was trying to think of good math puns this morning. I only came up with pre-calculus, but I mean it's pretty good, but I feel like there's more. If we use the variable mu, which is like a Greek letter, that would be great, but unfortunately it's not, it doesn't really show up in this class. So too bad. All right. So we're gonna graph this and we're gonna use the same process. I'm gonna find x-intercepts, y-intercepts, x-intercepts, vertical asymptotes, horizontal asymptotes. And it's also worth observing here that this function happens to be even. Not that we're real, we could totally check it, right? F of negative x equals 2 times negative x squared over negative x squared minus 1, which just becomes 2x squared over x squared minus 1 to the x. The nice thing about seeing that from the get-go is now we know that there's going to be symmetry across the y-axis. So the part on the right and the part on the left should look like reflections of each other, which helps. It makes it easier to graph with it. Let's do all the stuff. Y-intercepts. I'm going to set x equal to 0. We're going to get f of 0 is 2 times 0 squared over 0 squared minus 1. That's going to be 0 over negative 1, which is 0. All right. X-intercepts. You can set the whole thing equal to 0. But we saw before that setting the whole thing equal to 0 just becomes setting the top equal to 0. And hopefully you guys can see we're going to get x equal to 0. Let me ask you all. Let me show you on your fingers. What's the multiplicity of that intercept? Yeah, exactly that many. It is definitely 2, because x equal to 0 came from x squared equal to 0. I suppose I could have divided both sides by 2 first, and then like, oh yeah, it's coming from that. So this does have a multiplicity of 2, which means we're gonna bounce at 0, 0. So far we've got 1 point. Not super helpful. I mean, it's helpful, but we wish we had more, but that's what we got. So let's find the vertical asymptotes. And yes, there are more than one of them here. So we're going to set the denominator equal to 0. And although you can totally bring the 1 over to the other side, I'm a big fan of factoring. I'm going to factor this as x minus 1 times x plus 1. And we get x equal to positive 1 and x equal to negative 1. I think this is almost too great. And then lastly, vertical asymptote time, horizontal asymptote time. So our function 2x squared over x squared minus 1, the degrees are certainly the same. Degree on top is 2, degree on the bottom is 2. So the horizontal asymptote is going to be y equal to what over what? 2 over 1. Even though there's a lot of 1s happening here, I really would encourage you all to actually write that out when you do it. I know I said you don't have to, but I've seen people been like, oh, it's 2 because the degree was 2. It's not 2 because the degree was 2. It's 2 because the degrees matched and the coefficients were 2 over 1. So I want you to be very clear on why we're getting this value. And again, the real reason is because if you let x be very, very large or very, very negatively large, the fraction is going to get really, really close to 2. If x was 1,000, you'd have 2 million over 999,999, which is super close to 2. It's like 2.00000001. Very close to 2. I think that's it. So let's start graphing it, and we'll see if we need more information. Right? We might need an extra point or two. So I have the origin. Great. I have vertical asymptotes at x equal to 1 and negative 1. So there's x equal to 1. Negative 1. And then I also have a horizontal asymptote of y equal to 2. Okay. And now, so the problem with the origin is you don't actually know if you're above or below the x-axis because you're not. You're on the x-axis, which isn't above or below. So I don't know if as I move to the right here, if we're going to go up towards infinity as I approach this asymptote or down towards negative infinity. My gut would tell me I probably don't cross the horizontal asymptote. I don't have to, so I probably go down. But the easier way, the thing we probably should do just to make it easy is just pick a number. Pick a number between 0 and 1. I'm usually going to choose 1/2 if I have to pick something between 0 and 1. So let's plug in 1/2 and see that f of 1/2 is 2 times 1/2 squared over 1/2 squared minus 1. I don't really care about the value, but I'm going to find it anyway. I get 2 times 1/4 over 1/4 minus 1. That's going to be 2/4, which I know reduces, and 1/4 minus 1 is negative 3/4. And that fraction simplifies to negative 2/3. So it is negative. So I know that when x is 1/2, y is going to be negative 2/3. Which means now I'm forced to keep traveling down in this negative direction. Because as the x values get closer and closer and closer to 1, the y values get infinitely negatively large. What about the other side of 1? Are we also way down here, or are we way up here? Well, so the x-intercept bounces. But we're talking about the vertical asymptote now. And while I like what you're saying, it's actually not a bounce. So here's what you can totally do. And this is something I sometimes talk about, but not always. If you want to, you can look at the multiplicity of the asymptotes as well. So both of these asymptotes, x equals 1 and x equals negative 1, have what multiplicity? Well, x equals 1 came from x minus 1 to the first, and x equal to negative 1 came from x plus 1 to the first. These both have a multiplicity of 1. Okay, so big picture. For x-intercepts, when the multiplicity is odd, we cross. We go from negative to positive or positive to negative. When the x-intercept has an even multiplicity, we bounce. We stay negative or we stay positive. The same thing is true for asymptotes. If the asymptotes cross, we go from negative to positive or positive to negative because we're changing signs. If the asymptotes bounce, we stay on the same side. Both these are quote unquote crossing asymptotes. So we're going to cross from the bottom of the x-axis to the top of the x-axis. Now, if you don't like that, I totally understand, because I don't always like saying it. Another thing you could do, which is totally fine, is just to plug in like something like 2. If you plug in 2, f of 2 is going to be 2 times 2 squared over 2 squared minus 1, which is 8 over 3, which is positive. And here's what I will say. When the asymptotes have an odd multiplicity, what should I say? When it's only for vertical asymptotes. Right? We only talk about odd and even multiplicity for x-intercepts and x-asymptotes. We never talk about that for y-intercepts or y-asymptotes. Not a thing. But for the vertical asymptote here, if the multiplicity is odd, the function is on opposite sides of the x-axis. And if the multiplicity is even, the function's on the same. There's no good even same side where these are. So the function's on the same side, which we'll see an example of in the next 1 or 2 things. And now we could do all the same work for the left-hand side, or we can remember that the function's even. So the left-hand side should look like a reflection of the right-hand side. That's why we said that at the beginning, so because we don't have to do all the same work again. You totally could like plug in -1. Well, we know that it's going to bounce here, like so it bounces. So it bounces down like that. And then this is also an odd asymptote. So if it's down on one side, it's up on the other side. And this function looks like an even function. It looks like a reflection of itself in the y-axis. Yeah. Yeah. You totally can do that. The reason I'm not showing that is because I'm trying, again, as is typical, I'm trying to show you what I think is the most efficient way to do it. But totally, if you want to plug in a point here and a point here and a point here, that is super fine to see where the graph is going to be. And I definitely did that for some of the points. For the left-hand side here, I use the fact that we saw that it was, and again, so I'll be honest, when I'm graphing something, I don't look and see like, oh, it's even, oh, it's odd. Like I don't usually look for that. But if I happen to notice, I'm like, oh, great, I see it's even. That's going to save me some work. And I can just graph the right side and then the left-hand side just looks the same. So if you happen to see a thing like that, use it. Other questions? Like I saw like something about it. You know the scariest thing about this costume is? It's probably older than all of you. Like I wore this costume when I was a college student at UC Davis. It was pretty fun. Like it's a good Davis costume, right? We got cows. It's very on brand. What does that mean? Oh, okay. I thought you meant for me. All right. Okay. So, if you happen to be looking at the old notes on Canvas, but you don't think anyone is, but this next example is slightly different from what the previous example was. That's totally fine. So let's look at this function here. F of x equal to x minus 3 over x squared plus 2x plus 1. And we're just going to go through the process as we have been every time. Intercepts, asymptotes, a couple extra points. So let's look for the y-intercepts. So I'm going to set x equal to 0. I'm going to get f of 0 equal to 0 minus 3 over 0 plus 1. You could definitely skip that step, right? We know all the x things are going to be 0. It's just going to be the number on top divided by the number on the bottom. Great. X-intercept. We're going to really just want to set the top equal to 0. You can certainly take all the steps if you want and write the whole thing equal to 0. For a rational function, it's always going to boil down to just the numerator being 0, which is going to be x equal to 3. So my y-intercept, I should really be more specific here, is 0, negative 3. My x-intercept is 3, 0. All right, let's find our asymptotes. Vertical asymptotes. Again, we're going to set the denominator equal to 0. And I'm going to hope that factors. It does factor. How does that factor? Factors as x plus 1 times x plus 1. Okay, here's a place where it's easy to make a small error if you're not being too careful. What is my only vertical asymptote? Right. What's its multiplicity? It is 2, right? Because I really should be writing this as x plus 1 squared. Which means if the multiplicity is 2, so if the multiplicity is odd for an asymptote, things go opposites. One side's up, one side's down. If things are even, or I should say the multiplicity is even for a vertical asymptote, things are the same. Both sides are up or both sides are down. So we know what's going to happen here. It's either going to be up for a vertical asymptote, or it's going to be down. It's the same. And then we should find the horizontal asymptote. Let's see what's the degree on top. And I know you guys know. It's definitely 1. What's the degree on the bottom? Definitely 2. Wow. So that means the degree on top is less, which means our horizontal asymptote is what? Right. And I really do want you to think about this because this idea of horizontal asymptotes is not like going away. It's definitely going to appear in calculus next quarter. 1 second. The way I would really like you to kind of think about this is that, oh yeah, the horizontal asymptote is 0 because the fraction's denominator is getting much, much, much larger than the fraction's numerator. Question.
How do we determine that it's 0?
So the shortcut way, which is what we're using, is just by seeing that the degree on top is less than the degree on the bottom.
Oh, okay.
But the longer thought process is, oh, the reason for that is because the bottom is getting really, really big, much faster than the numerator. Again, my go-to big number is 1,000 for some reason. I don't know why it just is over the years. If you plug in 1,000, the top's going to be pretty close to 1,000. If you plug in 1,000 on the bottom's going to be 1,000,000 plus 2,000 plus 1. And 1,000 divided by 1,000,000, super small, like 0.001-ish. And it gets smaller as I skip through. So that's why we have but again, the shortcut is just that, oh yeah, the denominator's degree is larger than the numerator. That means the horizontal asymptote is going to be minus 0. And that's all I've got. So let's throw it all on the graph. So let's see, I've got the point 0, -3. I've got the point +3, 0. Notice, before I even start graphing, my horizontal asymptote is y = 0, and I'm definitely going to cross it because I have a point on the, and it is a cross, right? I forgot to say my x-intercept, the multiplicity there was definitely 1. So we're definitely going to cross at x = 3. Which brings up an interesting little thing we have to deal with. Well, yeah, I left myself enough room. I should have put this more centered. Oh well. And then we have a vertical asymptote at x = -1. And I don't typically try to draw the horizontal asymptote when it's on one of the axes. I'm just going to make my graph look right. And I'm going to say, yeah, y = 0, horizontal asymptote. But I don't think you need to try and draw it on there because the line it's already there. Okay, my plan of attack is usually to start at the y-intercept, if there is one, and move to the right. If I start here, if I move to the right, I'm going to have to hit that x-intercept. And then I have to cross it. If you like, we can plug in values, right? You can totally plug in 1. And it's going to be easier to plug stuff in if I think of my function in its factored form. If I plug in 1, what am I going to get on top? -2. And the bottom is going to be, I don't really care what the bottom is going to be, but it's going to be positive for sure. Because something squared is always positive. I should say always non-negative. It could be 0. So that's definitely a negative over a positive, which is negative. So we're down here, which we already knew we were. And it's going to look something like, I'm not going to graph it perfectly because I don't want to. Something like that. And that's going to cross at 3. Okay, but now it doesn't just go up and up and up because we have a horizontal asymptote at y = 0. So eventually this function has to get closer and closer to the horizontal asymptote, which means it has to turn around and flatten out. So if you cross the horizontal asymptote and there's nothing after, right, there's no features after that, right? This x-intercept is the last feature to the right, other than the horizontal asymptote. So once we've crossed it and they're like, oh, there's nothing else to stop me from going up, I just have to decide to turn around because the function gets closer and closer to 0 as x gets larger and larger. It's kind of funky. Well, I'm not sure what I'm not sure what you mean exactly. Okay. Well, but the thing is, so are you asking? Good question. Are you asking, can I do something like this? And then do that? No, I definitely cannot do that. Good question though. So why can't I do that? Well, a couple reasons. One, the function isn't always equal to 0, right? It's always going to be positive in this section over here. Because if you plug in something bigger than 3, like 4 minus 3 is positive, and the bottom is certainly positive. Right, but it's not flat because not all the values are 0. It's going to get bigger and bigger for a moment, and then it's going to decrease. Now, later on, when you all take calculus, you're going to learn how to find that point there, which is called a relative maximum. Right? It's the point that's bigger than all the stuff around it. For now, here's what I would encourage you to do. Rational functions are continuous. There's no weird breaks on their domains. So they're not continuous where you have a vertical asymptote. They're also differentiable on their domains, meaning when you hear the word differentiable, meaning you should think of it as being smooth. This function's smooth, it's differentiable. It's got no pointy points. It's got no weird sharp turns like that would be. So yeah, we can't just flatten out like that, unfortunately. We have to cross like we were told we were going to by the multiplicity of the x-intercept. And then we can't just keep going up. We have to eventually get closer to our horizontal asymptote. All right. Back at my y-intercept, if I travel to the left, are we going down or are we going way up? There's only one choice. You have to go downward. We can't go up because there's no x-intercepts to cross the x-axis with, right? We couldn't do that because, oh, there's an x-axis, we can't cross it. And then on the other side of this vertical asymptote, you have options. You could either say, well, we know from the multiplicity, it's either up, up, or down, down. But one side's down, so the other side's got to be down. Or you could pick a point, right? You could totally plug in something like -2, and f of -2 would be -2 minus 3 over -2 plus 1 squared, which is -5 over +1. So you could also do that, and that would be totally fine as well. Either way, you're seeing it's negative over here, so it's going to have this sort of shape. And then as you move away from the middle, you have to get closer and closer to your horizontal asymptote. Yeah.
That one doesn't like go up like that.
No, it doesn't. So, and you're asking a really good question. The reason I went up there and did this little thing is because I had to. Right? I had to cross the x-intercept at 3 because it was a cross. And then I had to turn around because I have to get closer to this horizontal asymptote. That's the whole deal with horizontal asymptotes. Once you're moving way out to the right or way out to the left, we have to get closer and closer to them. There's no other choice available to us. So my method of graphing this is kind of graphing by what I'm forced to do. I'm doing the things I have to do because there are no other choices available to me. Yeah.
I still don't understand why there's a maximum there.
Oh, there's a what? Sorry.
A maximum. I still don't understand why.
Okay. So I'm trying to think about how to answer it. We don't have options, right? So if I hit this point here at 3, if I plug in 4, did I plug in 4? No, I didn't. If we plug in 4, f of 4 is going to be 4 minus 3, which is 1, over, sorry, 4 plus 1 squared, which is, it's very small, right? My graph is very not to scale. If you plug in 5, f of 5 is going to be 2 over 5 plus 1 squared is 36, which is 1 over 18, which is a little bit bigger. So I want to point out 1/18 is larger than 1/25, right? Not by a lot, but it's bigger. So at 4, it's something. I'm not claiming the maximum is at 5. I'm just trying to give an example of seeing the function's getting bigger and bigger and bigger, but it can't get bigger forever. Why not? What's preventing me from getting bigger forever? The asymptote, the horizontal asymptote, right? Eventually, we have said the horizontal asymptote is 0, which means the function has to get closer, or not has to, it does get closer and closer to 0. Right? Once x is very, very large, the y values get super duper duper small.
How did you intuitively know that there was going to be a maximum there? Because if I were drawing it, I would kind of just like draw it close to the x-axis or the y-axis and just.
So again, I think we're kind of back in this question territory. I think you guys are asking, this is an extremely good question because you're getting really into the details. So here's 3. We come at 3, and then what? We have to cross. Okay, now what? Do I go up or down? You can't pick horizontal, right? The function is either getting bigger or smaller. Right? It's not just equal to the same thing all the time. So right, maybe it goes down really quick, but it can't have a sharp edge because it's nice and smooth. So, right, I could go down really like that, but it's again still, right, there's going to be a little bit of a maximum. So I have to have a point somewhere, sorry, where I am after 3. It does have to cross and get bigger and bigger and bigger, and then eventually somewhere it's going to top out because there isn't any other choice. There isn't any other way I can think to graph this, right? I can't do that because it looks wrong. And I can't like sharply turn like that because that's not allowed either. You have to have smooth looking functions.
The maximum is very small.
The maximum could be very small. Yeah. So certainly I would probably, well, in fact, yeah, we got a minute. Well, actually, we don't, but I'm going to show you something anyway. So I would agree that this maximum, I probably overestimated this. Like my picture probably looks a little higher than it actually. That's okay. Your values don't need to be exact. I want the shape and the important features. So let me all show you what this looks like, just so you can really see it. So you're not like, James is a liar. If I can find the thing. So I really encourage you all to take advantage of your ability to look at graphs of things using Desmos. It is nice. And on the bottom, we have x squared plus 2x plus 1. So take a look at that. So check it out. Oh, that looks wrong because I got the 1 in the wrong spot there. Sorry. So check this thing out. You might think, oh yeah, James, that looks super duper flat. And it does. My drawing is an exaggeration for sure. But I will tell you, look, the y values are getting bigger, 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 bigger. They get bigger for a while, and then they start getting smaller again. So somewhere in there, maybe it's 6, I don't really know. There's a maximum. It's a very small maximum, but you should draw exaggerate because I don't care that it doesn't look exactly right. So the whole point is there, you should know that, oh yeah, it's going to cross, it's going to get bigger. Okay, it's getting bigger very, very slowly, and then it gets a bit smaller afterwards. But it is going to cross and then turn around. But yeah, so I feel like you've made a good point, right? It is definitely, my graph doesn't look perfect. Your graphs don't have to look perfect. I want to see the features. I want to see the behaviors. I don't care that the values are off a little bit. Can I zoom into what? Well, so like, you mean like, I feel like you're talking about this part that I've drawn like over here. Yeah, so I know that, right? So I also was kind of running out of room, right? It's probably a little bit more of a it's definitely more of a gradual sort of like, it's probably more like that. What I am graphing is something called the concavity, really. I know that to flatten out like this, it has to go from being concave down, where it opens in a downward way, to concave up, where it opens in an upward way. And I drew that somewhat exaggerated.